welcome everyone to this Europlanet webinar. It's the second one that we are doing. NUCLIO, my institution, is doing in partnership with Europlanet. And today we have several privileges. We have the privilege of having some students with us from Portugal and from Mozambique, and I hope from some other sites start to appear as well. And we have the privilege of having with us Athena Coustenis. I hope I didn't mispronounce your name. Athena is from the Observatoire de Paris-Meudon in France, and she is a planetologist, director of research at CNRS. And she's going to be sharing with us the latest news about the exploration of our solar system. I saw some of the slides. It's very, very exciting. And I hope that you enjoy. And if at any point you have any question, anything you would like to ask to Athena, please interrupt us. Just put your question here on the chat, and we'll be very, very glad to welcome your questions. By the end of the webinar, I will promote you all to panelists, so you, Athena, will be able to see also all of you. Okay, Athena, welcome. Thank you very much for accepting our invitation. And I would like you to introduce yourself and tell you just a little bit about yourself to the students or the participants watching us.
Absolutely. Good morning, everybody. I'm very happy to be with you here today. I'm actually today in Athens, Greece. The weather is very nice, but I'm located essentially at Paris Observatory in Meudon. I don't know if you can see my pointer, but this is the place that you see down here in my first slide, where you see some small telescopes and trees. So we have a very nice environment to work with. Unfortunately, the objects we observe these days are very far away, and the pollution from Paris doesn't make it possible to observe with these telescopes anything that is further than our solar system. But we have a very nice environment in which to do, essentially, for my part, planetary science. So planetary science is basically the study of our solar system. And we study the solar system for many reasons, also because we have unique objects in the solar system, but also because, as all of you know, since ancient times, everybody is asking the question, is there life elsewhere than the Earth? And so today's actually lecture is not going to bring you the answer to the question, but it's going to give you some elements about how the astronomers, how the astrophysicists attack this question. I have devoted quite some time of my career in looking at other objects in the solar system where we might find what we call habitable conditions, and I will tell you what habitability is for an astronomer. But we're going to be focusing, as the title of my seminar says, to moons. Moons are satellites around planets, and in this case, we're going to go to the outer solar system. So here's today's menu, okay? So you're going to this restaurant and you're looking at the menu, and what are we going to do today? We're going to look at some things, like, for instance, what is the outer solar system? How do we get there? And if I'm thirsty, where do I get a drink of water in the outer solar system? How do we manage sometimes to land on a comet or launch a rocket? And then we're going to dive into a strange world where you would have some benefits. You would feel lighter, younger, and less stressed. We're going to ask ourselves the questions, are there lakes elsewhere than on Earth? Are there geysers elsewhere than on Earth? And then we're going to be saying goodbye at a very special and faithful mission we've had for quite some time. And then we're going to be looking at new ones, because every time there is a death, there is also new life coming on. So this is today's menu. And I'm going to start with our outer solar system. I don't have the access to remove my video at this stage. When we need to remove it, Rosa or Telina, you can perhaps do it.
That's okay. It's good that they see you as well, Athena. That's perfectly fine.
If it falls on any precious images, you can remove me.
No, it doesn't collide with the image. Don't worry.
Okay, so our solar system, as you all know, it's a very, very diversified environment. We have the terrestrial planets, the small ones close to the sun, and then we have what we call the giant planets that are much, much bigger and further out from the sun. And you can see they're numbered up to 8 on my slide, but there used to be 9 of them. As you all know, we also had Pluto. Pluto, who is currently being investigated by a wonderful mission called New Horizons. But unfortunately, Pluto lost its place among the 9 planets and has become a dwarf planet in the recent years. We are going to be focusing on the giant planets' environment over here, and in particular 2 of them, 2 giant planets that have an immense amount of satellites each. Each have more than 60 moons around them. And this is where we find some conditions very, very special and very specific for habitability in the solar system. So these are the giant planets. You recognize Jupiter, Saturn, the Lord of the Rings, and then we have Uranus and also Neptune. And these giant planets were investigated some time ago by the Voyager missions. The Voyager missions were amazing robots flying in the 70s and 80s throughout the outer solar system, and they had provided all the images we had up until recently. But now we've done better. In the meantime, we have discovered fantastic, unique worlds around these giant planets. And these are the satellites. And you see here the satellites, major satellites of Jupiter, Saturn, Uranus, and Neptune. Neptune, of course, everybody has heard about Triton. Uranus has also some large satellites and arcs of rings. And Saturn has this big, big satellite called Titan. But it's not the largest satellite in our own solar system, because the largest satellite is Ganymede. Ganymede is around Jupiter. So we're going to be looking at these satellites because we're going to be investigating the conditions for habitability. So I'm an astronomer, I'm not a biologist. I wouldn't be able to tell you how to make life. Not even biologists actually do these days. But as an astronomer, what am I looking for? Well, the conditions that we find on our own planet that are favorable to life is liquid water, essential elements that we call the SNOPs for carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, so that we know that these are the elements that make the molecules that constitute life on our own planet. But we also need energy. If you don't have energy sources, you cannot, for instance, produce the heat in the planet that is requested. You cannot initiate metabolism. You need energy sources. And all of this has to happen in a stable environment so that metabolism and life has time to emerge and develop over time. So these are the 4 requirements that I'm going to be looking for. And essentially, it's water, SNOPs, that's the nutrients, and energy. So where am I going to be able to find these things? Well, we have what we call the habitable zone. What is a habitable zone? Is if you look at this diagram, it may seem complicated, but it's not. You have here on the left side different kinds of stars with different masses, starting from half the size of our own sun to twice the size of our own sun, for instance. Our sun is here in the middle, and you can see our solar system. Habitable zone in our solar system is this blue area where you can find liquid water on the surface. So far, we had always been looking for liquid water on the surface, or traces of liquid water on the surface. And for stars of different sizes, the smaller the star, the closer is the habitable zone to this star, because this is where you can have enough heat to have liquid water on the surface. And the larger the star, the further out you can find the habitable zone where liquid water can exist on the surface. Oh, look how funnily, the only planet within the habitable zone around our star, right in the middle, is our Earth. So we are at the right place at the right time. Mars and Venus are objects that could have developed life in the past, but today they're both outside the habitable zone. But some time ago, there was a discovery, because we thought there could not be liquid water anywhere else beyond this habitable zone. There was a discovery on a little moon around Saturn. You can see here these geysers, this ejecta, these plumes coming out of Enceladus. And this discovery meant basically that there was liquid water underneath the surface of some other bodies at much, much further distances from the sun than initially thought. Yes, the water is not on the surface. And we're talking about deep habitats in this case, not surface habitats. Deep habitats means that around Jupiter, as around Saturn, as is shown here, you could have regions of liquid water underneath the surfaces, either in direct contact with the core and ejecting into space, as is the case for Enceladus, or trapped somewhere underneath the surface between, for instance, two ice layers. So our concept of the habitable zone has expanded and is now going all the way out to the outer solar system and probably beyond. And this is where we're going to be looking for liquid water, essential elements, energy sources, and stable environments, and asking ourselves the question, are icy satellites like the ones I just showed you, Ganymede, Europa, Enceladus, or Titan, possibly habitable worlds? So the answer is that today we think we have evidence for the presence of liquid water oceans in several places in our solar system, including on Mars in the past, not today, but the space missions are showing that there could have been liquid water on the surface of Mars a long time ago, on Europa, on Enceladus, Ganymede, and Titan. Here is the Earth by comparison. And there is one thing that people don't realize immediately. The water on Earth constitutes 0.02% of the total volume, as it said here. So I'm going to calibrate this to 1. If this is 1 for the Earth, Mars in the past might have had twice as much liquid water on its surface as the Earth. But the interesting part is that in the outer solar system, the factors increase dramatically. On Europa, underneath the surface, today, you may have as much as twice the amount of liquid water as on the Earth's surface. On Ganymede, you could have 6 times as much. On Titan, you could have 11 times as much liquid water underneath the surface. This is what the models are telling us, and this is what we call ocean worlds. That is, worlds where you could have liquid water much, much more than on Earth. Yes, underneath the surface, but the amount of liquid water is immensely higher than on our own planet. So if you look at some of these moons, basically what you need to understand is that if some of these bodies evolved to a higher life form on the surface, this is the case of our Earth, and it could be the case in other planetary systems, which we call exoplanets, Mars and Venus may have developed some form of life, but it didn't get very far because of the conditions on these two planets. But in the outer solar system, you could have two sorts of satellites, one with the liquid water underneath the surface, but in direct contact with the core of silicates. This is the case of what we have on our own planet, and it produces energy. In some other cases, like for instance for Ganymede or Titan, the liquid water is included, sandwiched between two ice layers. So these are two different categories of icy moons as possible habitats. On the one hand, Europa and Enceladus, where you see that you have contact both with the mantle outside and the silicate core, similar to what we have on the Earth, so the energy sources must be there, or Ganymede and Titan, in which case the liquid water is sandwiched between two ice layers. The question is this true? Are our theories valid? And how do we explore them, these satellites, to find the answers to our questions? So we explore them, of course, with ground-based telescopes, every means we have, observatories around the Earth, but of course also we use space missions. In the case of the satellites around Jupiter, Europa, Ganymede, and Callisto, we've had the Galileo mission. The Galileo mission went there in 1995 and worked until 2000. And most of the information we had up until very recently was from this space mission. Around Saturn, for Enceladus and Titan, for instance, we have the wonderful Cassini-Huygens mission, about which I'm going to be telling you more afterwards. And this is still there in the system making observations. And this is what revealed these worlds to us. I couldn't resist showing you, because I'm going to say a few words about Jupiter's system. As I announced in my titles, the icy moons around Saturn are wonderful. I'm very biased, but they're also wonderful worlds around Jupiter. But I couldn't resist showing you some of the most recent Juno images. Juno is the mission that is now around Jupiter. It has as its main target the planet, Jupiter. And what you see here is a whole host of different images, different aspects of the planet as it turns. And you can see all these magnificent manifestations of Jupiter's atmosphere with a great red spot turning around, but also indications of storms, as you can see down here in the southern hemisphere. Look at this beautiful image of the southern hemisphere and these storms raging in the southern pole. And all of these were captured by the camera on Juno, JunoCam. And there's more to come as the interpretations are taking place. So in the system of Jupiter, we have four large moons, the Galilean moons that I described before, but there are three large moons that we need to explore if we're thinking about habitability. One is Ganymede. Ganymede is the largest satellite in our own solar system, the biggest one. And we think it may have a deep ocean. If you look closely on this image, you can see this darker blue line inside its interior structure. And this dark blue line is actually the hydrosphere. What we call a hydrosphere is the ocean of liquid water. You can see it sits between two brighter blue areas, and these are the ice layers between which this liquid ocean, water ocean, is trapped. The Ganymede satellite is not only the largest one in our own solar system, it's also unique because it has an internal dynamo and an induced magnetic field. And the magnetic field is what protects us today on Earth from the emission and the radiation that comes from our sun. This, with the help of the ozone layer, this is what has allowed for life to evolve and to survive on the Earth's surface. So another moon in the Jupiter system is Callisto. Callisto, we don't know much about what's underneath its surface. We don't know if it has differentiated. That means whether it has different layers constructed in the same way as Ganymede does. But we know it has a very, very ancient surface, and we want to study it because it gives us some information on the early ages. And of course, everybody has heard about Europa. Europa, this world that was the first one in the outer solar system for which we thought there was an undersurface ocean. You can see it here. And in this case, this undersurface ocean is not trapped between two ice layers. It's in direct contact with the silicate core and with probably the mantle very close to the surface. Excuse me. And this is what will allow us to explore it thoroughly in the future, because all of these moons around Jupiter have something to show us. They have something to teach us. But the closer a moon is to Jupiter, the hotter it is, the hotter in its interior. Look at poor Io here. This is Io. 400 volcanoes on the surface. It's amazing that this world manages to survive with all these explosions, but we certainly cannot consider it for habitable conditions. But Europa, Ganymede, and Callisto that follow have dynamic movements of the surface possible, tectonics, and this is another source of energy. And you can see their surfaces and everything else and how they evolve. The furthest they are away from Jupiter, the more protected they are, because Jupiter's radiation field is something enormous and it's very damaging to anything that comes on the surface. This is why I mentioned the magnetic field around Ganymede before, because this is what protects Ganymede from the cosmic rays, but also essentially from the particles from Jupiter and its radiation field. So here are these three moons we'll be looking at with their internal structures indicating the possible existence of a liquid ocean. How do we know this? This is on the top, you have a Galileo emission image of Europa. And at the bottom, you have an image of the Earth. And when geologists look at this, the upper left image looks very much like what we have on our own Earth when you go to the Antarctic Ocean and you look at a frozen sea. Why? Because the pieces of ice that float here seem to produce similar structures and similar pictures as the one that we see on Europa. And so the resemblance of these two images leads the scientists to think that there is perhaps a liquid ocean underneath Europa, which at some times was actually at the level of the surface, creating all these different structures in the same way as at the Antarctic Ocean, when it freezes out, we see these pieces of ice that used to float frozen right there on the surface. So we think there is a liquid water ocean underneath Europa's surface because of these evidences, these cracks that we see on the surface, but we still don't know what exactly is the composition on the surface of Europa. We have different observations that we try to match with what we produce in the laboratory. However, as you can see here, the different observations in blue and in red gotten from the NIMS instrument on Galileo do not match exactly either pure ice or other constituents that we could think we would have on Europa's surface. So we do not have today a complete image of what's on Europa's surface, but we saw also very recently some plumes, some geysers coming out of Europa's southern pole as observed by the Hubble Space Telescope. These observations need to be confirmed, but you can see again here evidence that perhaps Europa is active in the interior, does not only have a liquid water ocean, but also has geysers. So very interesting, Europa. Europa is actually one of the places that we may have some conditions of what we call hydrothermal activity. This is what we have on our own planet in the deep oceans. It's the black smokers. These are places where we have contact with the silicates, and this produces methane and other species, and heat. And this is what allows some very strange beings on the earth, inside the earth, to survive at the depth, very, very deep layers inside the oceans of our own planet. And on Europa, one might imagine, you see here this little beasts again. I don't think we have exactly those on Europa, but you can see here that there is some indication that microbial life, I would say, and not as developed a life as this one shown here, could exist at the depths of the oceans on Europa. The question is, how do this get to the surface where we have the contact with organic material produced there? And is this organic material, these oxidants, how does it survive the radiation from Jupiter's magnetosphere or Jupiter's radiation field? There is no protection with a magnetic field on Europa. So we don't know exactly what's happening there, but we have a liquid water ocean and possible hydrothermal activity, and we do have a stable environment in the case of Europa. Very interesting. We need to go back and explore. Ganymede also very interesting. As I said, no direct contact with silicates, but liquid water trapped between two ice layers of different thickness and of different pressure conditions. And so here you would need different instrumentations and measurements to see if you could bring organics from the surface inside, deposit it on this liquid water ocean, and would anything alive survive there? And now I'm going to turn to the Saturnian system. The Voyager missions here are the ones that gave us most of the information we have about the Saturnian system, the planet, and its satellites. The Voyager mission encountered Saturn, got in that system in 1980, and produced many images that told us one thing, essentially, that we really needed to go back with a new space mission, more adapted for such a complex system. And so the Cassini-Huygens mission came together. It's something we developed a long time ago. All of the images I'm going to be showing you from the Cassini-Huygens mission are real ones. Sometimes you think we did something special to get, for instance, such an image with the 3 satellites, 4 actually, and the planet in the same image, but we didn't. These are amazing images taken by the Cassini spacecraft. And the Cassini spacecraft is a wonderful mission. You can see here the spacecraft with the 12 instruments on board, the antennas, and the 6 instruments on the probe, the Huygens probe, that was actually constructed, built by the European Space Agency. And here I've put just a diagram of that we put together. The people like myself who have worked on this mission since the beginning, we gave it human functions. So you can see here, for instance, that the antenna is what would represent a cell phone today, but because who goes out anywhere, let alone the outer solar system, without their cell phone today? And this is to transmit the data back to the Earth. You have the eyes that are the cameras. Back here, there are more eyes. And here is a baby. I'm sorry, I'm sitting on top of it, but yeah, the baby was the Huygens probe. For us, it was a baby because we constructed it, we built it, we put the instruments on board. We somehow gave birth to this whole mission. I worked on this mission since the very beginning in the 90s. And from that day until today, it's been a pleasure and a privilege to work on this space mission. Amazing spacecraft that flew by the Earth, twice by Venus, to get to Saturn in 2004 and make some wonderful images, like, for instance, from the planet in the North Pole. You can see here a storm again raging at Saturn's northern polar region. in this special form of an hexagon that took scientists a long time to figure out in the laboratory how to produce. But Cassini-Huygens essentially revealed two of the moons, Titan and Enceladus, on which we saw amazing features, some of them very similar to what we have on our own planet, some of them very, very different. And we created a whole new science in planetology by studying these two moons. So for instance, on Enceladus, we saw the geysers that I mentioned before. But what is very important about these plumes is that there is the presence of organics, water vapor and organic material inside them. And this is very important. First, because it says that yes, indeed, there's liquid water underneath the surface and very close actually to the surface. Second, because you have organic chemistry. And remember that the schnapps, the famous organic chemistry material that you use as nutrients, is present on Enceladus. And so we have confirmed that the habitable zone is extending much, much further than we thought before. And we have organic material on Enceladus, and we have energy sources, because if you see geysers, there's energy beneath them. These are cryovolcanoes, and they're created by a lot of energy present in the inside. And of course, the wonderful thing is that with Cassini, we plunged right through these plumes. Sometimes we got as close as 25 kilometers from the surface. Very risky thing to do, because the attraction of the moon could have brought the spacecraft down, but it didn't. And so, as my friend Chris McKay says, the nice thing about Enceladus is that you can fly through the plumes and get a taste of the material directly. You don't need to dig, you don't need to do anything. You just fly through, pick up the material, and see what it's made of. And the plumes come out of the southern pole of Enceladus, where we have what we call the tiger stripes. The tiger stripes are very deep, deep canyons. And you can see that these canyons actually here show evidence for very, very high temperatures. So this is very interesting. We have high temperatures, we have energy sources, we have water vapor coming out, so there's probably liquid water underneath the surface. And all of this is there to be sampled directly from a space mission. And even more important, I would say very recently, maybe you've seen this in the papers, there has been the discovery of hydrogen. And this leads to the thinking that there is hydrothermal activity on Enceladus underneath the surface, as you can see here, hydrothermal vent. And of course, the imagination of people has run wild, because then perhaps we have discovered hydrogen, we have carbon, we have liquid water. Oh, maybe we could get microbial life evidence like in extreme environments on Earth directly. Personally, I think we need a little bit more observations. We need some more measurements, and it doesn't necessarily mean because we have discovered hydrogen that all the requirements are there for life, but they're certainly there for habitable conditions. So Enceladus, very, very nice, very enticing, very unique. But so is Titan. You can see here Titan right behind the rings of Saturn. And Pan is the other satellite that you have here on top on this image from the camera of Cassini. And Titan is amazing because it was discovered so long ago by Huygens in 1655. And we knew already about the presence of an atmosphere around it. We didn't know exactly what the atmosphere would be made of. And I'm going to be discussing many of these things that you see here. But one item that you might want to pick up is that, for instance, the gravity is 7 times lower than on Earth. So I promised you a place where you would feel lighter. So on Titan, you would weigh 7 times less than on Earth. So anybody having issues with their weight, like myself, when I go on a diet, I would perhaps do better to go on Titan. Also, we have on the surface of Titan the same conditions as pressure goes as on Earth, 1.5 bar. On the Earth's surface, we have 1 bar, 1 atmosphere. And we've made continuous measurements of Titan's atmosphere and conditions for quite some time. But more importantly is to think also in terms of time, because Titan has seasons as it follows Saturn on its orbital, on its orbit around the Sun. But a year on Titan actually is 30 Earth years. So a season is 7.5 years. So 30 years means that on Titan, some of you would not even be 1 year old, basically. So you will feel also much, much younger, right? And for those who stress about the work you need to do in 1 day on Titan is 16 days. So you have 8 days for morning to work, to get your work done, and 8 days to sleep. So I'm not saying this just for the fun. I'm saying this because try to think in different time constants. It's very important to realize that on some other worlds, even with similar things that we see on our Earth, conditions might be very different. So Titan is a very enticing place, which also has another tremendous advantage. The major gas in its atmosphere is nitrogen, molecular nitrogen. And what do you think you're breathing right now on Earth? You're breathing nitrogen, 80%. Everybody says oxygen. No, oxygen is less or somewhere around 20%. You're breathing nitrogen. And nitrogen is the major constituent. Also on Titan, there's very little oxygen, unfortunately, but you have methane, which in combination with nitrogen produces hydrocarbons, nitriles, and other organic constituents. We also have the temperature inversion. This is where the temperature stops decreasing and increases again towards the surface. It's due to a greenhouse effect, same thing as we have on our own planet. But the surface temperature, okay, minus 180 degrees Celsius. So you would need warm clothes to go there, not much oxygen, and we still don't know what the surface on Titan is made of. But Titan is still the best case, the best analog we have at the dimensions of a laboratory at planetary scale to help us understand what was the primordial atmosphere on Earth in the beginning before life came on. And this is because the oxygen on our own planet was produced by life, essentially. And before that, we think the conditions were very similar to what we have on Titan. So studying Titan takes us back to the past of our own planet with all this complex and very, very intense organic chemistry that we have in the atmosphere that starts from the higher levels and then goes with higher complex, high degree complex organics all the way down to the surface. And these are the measurements made by the Cassini mission at different levels in the atmosphere, showing that we do have the nutrients necessary on Titan. We also have an amazing surface on Titan on which we find, among other things, we find dunes, we find channels, and we find also lakes, which currently are located in the northern polar region. So I wanted to show you a little movie, if I can play it, about a lake on Titan, and I'll let the people speak
Titan
in there.
is the only planetary body besides Earth that we know has lakes. At 290 degrees Fahrenheit below zero, the only liquid that makes sense there is a combination of methane and ethane. This lake is Ontario Locus in Titan's southern hemisphere. It's a little smaller than Lake Michigan. We've colored the lake black because we think that's probably its real color, although we don't really know for sure. We've exaggerated the heights of the shoreline features to make them easier to see. Notice these hills, probably made of water ice. See how the liquid has flooded up the valleys? Further north is a long, smoother beach that looks like it's been shaped by waves. You can see some lines along the beach that might be old shorelines, like bathtub rings. So we know the level of the lake has changed. Now we're turning east to a very obvious bay that cuts into the beach, so it's likely to be younger. We'll cross over the lake. You'll see some flooded valleys, and in the background is a large river that makes a delta, like the Mississippi River. Its shape means the lake is shallow and the river is slow. Ontario's shore is surprisingly like earthly lake shores. Pretty amazing to find something this Earth-like 800 million miles away.
Yes, everything you saw in this movie is actually put together from real images taken from the Cassini spacecraft and the Huygens probe. You can see here the trajectory of the Huygens probe as it went into Titan's atmosphere and landing on the surface by using 3 different parachutes. And this amazing probe got on the surface and sent us signals back to the Earth for more than 3 hours. Actually 5 hours and more, including 3 hours from the surface. When all the engineers had convinced us it would crash, this probe landed very nicely on a very smooth surface. So all the images you saw before, like this one, for instance, where you see channels up here in a part very close to where we landed, these channels and this dark area here are probably formed from liquid methane. Actually, at some point, at some season on Titan, there is a flow of liquid hydrocarbons. So it's very important to realize that this is a world that changes with seasons. Very important to see that the images we got from the surface here, for instance, indicate the presence of a riverbed, and you have these pebbles, these round things, also indicative of flow that are probably made of water ice, and they're all at different dimensions. And here's now the Huygens probe sitting on Titan's surface. It's probably going to be covered with the organics that fall through the atmosphere, but not yet, not just yet. We still think we have the probe on the surface and visible. Just to indicate that there's also a lot of evidence for energy inside Titan. We have some regions that show indication of cryovolcanism, volcanoes on Titan. We would love to catch one of them actually in action. So we're looking for that. And there's quite some evidence of the presence of the undersurface liquid water ocean in the interior of Titan. All this evidence comes from measurements by the Cassini and in spacecraft and the Huygens probe. So I mentioned the seasons on Titan. During the 13 years of mission, Cassini will only have monitored actually 2 seasons. We still have 2 seasons on Titan that we have never seen. We see many changes with season on Titan. So it's clear that Titan is a very, very high potential for astrobiology. It has all of these features on the surface and in the atmosphere that I already discussed, on top of the climate and the seasonal effects. So it's very interesting to study in the future. So I think I would like to show you now something of what is going to happen next, right after now with the Cassini mission. We're getting in what we call the grand finale, because for such an exceptional mission, we really need an amazing end. And the grand finale is something that has started already since the end of last year, with several orbits going first through the F ring of Saturn, but then also starting in April 22, we did our last targeted Titan flyby, that is the scheduled Titan flyby, that puts us on a trajectory that produces puts us on the trajectory for the grand finale, that you can see here how we're flying up and down in high elliptical orbits, very high elliptical orbits. You can see how we're going around the planet. You have to get in the right trajectory to be able to fly through and plunge through the rings, which is what we expect to do in the end. We also, since April 23, have started the last 22 orbits and 9 non-targeted Titan flybys. And on April 26, we did our first dive of the 22 periapsis between the innermost ring and Saturn. And one of the basic results was we didn't see as many particles as we thought we would see. at the time. So it's a very clear zone. Saturn has actually eaten up all the material in there. So September 11, we're going to do our last non-targeted Titan flyby. We get on an impact trajectory to Cassini, and then we go into Saturn for impact on September 15. And this is what this is going to look like, plunging between the planet and the innermost ring. You can see it's a very scary event. Every time we do this, we take a high risk because we may be captured by the planet itself before we finish, or we may be hit by particles and then the instruments won't work. But we have these 22 flybys through the gap that you can see here that have already started. We're in the 5th one. And so we will do some unique observations of the rings. You can imagine the high resolution we're going to get. We're going to do also measurements of the mass that exists in there and look at the ages of the rings with high radio occultation imaging. And also we're going to be looking at Saturn for polar observations and auroras. And these are just some of the images of the satellites we're going to be getting. And also the rings. Look at the higher resolution images. Look at the amazing resolution and detail we're going to get. And then we're going to end up in Saturn. We have planned this. This is a fit end for this amazing mission. We're going to get information for as long as we can when we fly into Saturn to get indications and information on dynamics, composition, structure, and so on. So I'm going to end this by playing you a movie about this wonderful end of the Cassini mission that we're expecting, and I'll let you enjoy this part of this movie.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
And liftoff of the Cassini spacecraft on a million-mile trek to Saturn. We have cleared the tower. The program is in.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
So I burn attitude, pointing position, light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system. For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
So I would like to remind you all, 15th September, please be with us when this event will happen. I'm sure you'll hear more about it in the news. I just wanted to end by saying that there are other concepts for returning to Titan, including an air balloon and landers. So there's a lot of imagination and work to do for young people who have ideas about future exploration in the outer solar system. There's also a space mission called JUICE that is going to go to explore the moons around Jupiter. So all of this in the purpose of looking for habitable worlds in our own solar system, but not only, also very representative, these icy moons are of the exoplanet worlds. And so we are in a time and age of the future exploration where with JUICE and Cassini, we've brought forward a lot of revelations for these bodies. So in the future, we're hoping to get more with space missions, but also with ground-based measurements after the first discoveries. And in the future, we hope to do some landings on these worlds. So I give you a rendezvous appointment on 50 September 2017 for this amazing end of mission. And I thank you very much for your attention.
Athena, amazing, amazing. I'm so full of questions and things I would like to ask to you. I completely adored your presentation, but I will make sure that I give to the students the floor first. So I will promote Cesar and Sonia to panelists. I hope you are okay with that. If there is any problem with the schools, please let me know.
No problem.
Okay, and Sonia. Okay, I will promote everyone. If you don't want, you just can go away. So everyone now is a panelist, so that means that we can see you all. Athena, maybe you can stop sharing your screen so that they can see you better. Exactly. So if any of you don't want to be seen, please just stop your video and we won't see you there. I see all the kids waving to you. If there are any questions, please just come forward and ask your questions directly to Athena. It's great to have you there. I see the kids in Mozambique waving at us, at you.
Or ideas for missions. Don't hesitate to give me ideas.
Yeah, that's very good, because you know they are the future scientists. Absolutely. For sure. Huh?
I would just like to make a comment for the young people. When I started working in this business, I worked with the Voyager data. Remember I told you the Voyager missions were in the 80s. And I think I wasn't working that early, but with the Voyager, we did one flyby, and we were working on the data 10 years later. With Cassini, we got so many flybys that I think 3 generations of astronomers are certainly going to be working on the data 30, 40, even 50 years from now. So we're all counting on you.
So there's a question here saying, actually from Zé Gonçalves, he's not here right now. It's saying if it is possible to send a human mission to those moons.
So for the moment, as you may know, we are looking to sending a human mission to Mars because in the next 10 years or so, we think we would be capable to send somebody to Mars. A mission to Mars takes about 8 months. And a mission like the one I showed you to the outer solar system with the instruments and the people on board would take 8 years. So we're thinking about it, we're considering it, but I don't think that right now we can send somebody.
Why it will take 8 years?
So, for instance, Cassini took 8 years because you need to do all the flybys to gain the energy that you need to actually arrive at your target when you carry a lot of weight. Even if the astronauts are not very heavy, they will need equipment, they will need things on board to help them survive the 8 years or the even 5. Even if it were 5 years, it's still, you know, a considerable amount of time. So we don't know yet, medically speaking, how we can do this, but the doctors who work with astronauts actually are telling me that we have some experiments on animals that we put into some sort of sleep for quite some time and wait to see if they wake in a good condition. So Mars is, I think Mars is around the corner. Getting to the outer solar system, because as I said again, you need the energy and the power for the spacecraft to take it so far away, either with solar energy or with nuclear power, but somehow we also use the kinetic energy to do flybys around planets and gain the energy that we need to bring it so far out. It's going to be at least 5 to 8 years.
And so you said that you've been working on the mission, the Cassini mission, for quite some time now. So how long does it take to, you know, since the very first idea someone have, oh, I'm going to design this mission to Saturn, until today?
That's a good question. It takes a long time, especially for a large mission. Cassini is a large mission. It cost at the time around $3 billion. Okay, you need to build the spacecraft. You need to make it right, to find the trajectory, to build the instruments, to put everything on board. And then it's still not finished because you need to have the operations, the scheduling, the people who work behind the mission. There are very many people. Now, I'm not talking just about the scientists, okay? I'm talking about the engineers and the people who survey the spacecraft. So for us, the idea started in the mid-80s, and we started development and making the proposals in the 90s. The launch was 97, the arrival was 2004, and the mission was going to last just 4 years. 2008 was going to be finished. And look where we are today. Almost 10 years more, so we can't complain. So the mission lasted for 13 years total. So it pays off. In the end, it pays off, even if it takes a long time to build.
And so you said lots of people, and it's all types of professions that have to be involved in a mission like this, right?
Absolutely. Yeah, within the scientists already, within the scientists, we are atmosphericists, planetologists, biologists, geologists, physical scientists, people who work with the Earth, just to look for the habitable conditions I was describing. And then the engineers, you need all kinds of engineers. You need all types of people who construct, who build the instruments themselves. I think somebody mentioned to me that there are more than 10,000 people working behind Cassini.
Wow, 10,000. Wow.
Yes.
Wow. Okay.
Yeah.
And so another thing that is interesting to me is that it's decided that the spacecraft, which by the way is so tiny when you see in comparison with the you know, you think it's such a big, but then you see the movie, it's such a tiny thing, but then it will crash on the surface of the planet. And can you explain to us why you decide to do that and not to leave that forever?
So you cannot leave it forever, because once the fuel has run out, it could do anything. It could go out of the trajectory. It could hit another one of the satellites. And as I was trying to convince you, some of these satellites are very interesting for life. So we don't want the spacecraft to go hit there, because it would contaminate the satellite. And if we want to explore those satellites, we need to do it the right way. It's called planetary protection, and you have to go with a special spacecraft that is sterilized. You have taken all the precautions, right? And so we don't want it to go someplace else. So the safe thing is to push it inside Saturn's atmosphere. It will travel through the atmosphere at very high pressure levels. We are taking bets. How far deep can it go? 1 bar, 20 bars, 100 bars, no. And then it will return the signal to us as far as the instruments, as long as the instruments can work, okay? And then it will disintegrate, because the pressure inside will become very high. And then, as the movie says, the mission will become part of the planet. It will become one with the planet, and we'll have all of that in there. But before it disintegrates, we're hoping we'll get a lot of information on things that we would need a probe to do. If we could send a probe into Saturn to make these measurements, okay. But here we're going to do a double mission. We've done Cassini, actually triple. We've done Cassini, the spacecraft studying the whole Saturnian system. We've done the Huygens probe going into Titan. And now we're going to throw Cassini inside Saturn, and it's a third mission. We're doing a probe into Saturn.
That's amazing. That's really amazing. I'm looking forward to further results. And I think we're reaching to the limit of the time we took from you. I know you are busy in another conference. Thanks so much for the time and the amazing conference that you gave to us today. Is there any other question coming from the schools or anyone in the audience? I don't see anything else written here. In any case, there will be this session is recorded, and I know that Athena will be available to answer further questions if they appear. It was a true privilege. And,
I really want to say we're counting on all of you, the young people, but also the teachers and everybody, because for us it's very important for people to disseminate this amazing. We love to share with the public. In our work, we don't want to keep these things for ourselves. So thank you all very much for attending today, and all of those who will see it later on. It's a pleasure for me.
So for information, we will work to add subtitles in Portuguese, for instance, maybe in other languages as well to this webinar, so it will reach out to a lot of teachers and students. So
absolutely. See you.
Thank you. Thank you very much, everyone.
Thank you. Bye-bye.
Bye.